So thank you for the opportunity to talk today. So I'm an instrument scientist on the Reflectometer at ICIS Neutron Source, and my background's in physical chemistry. And today I'm going to talk to you about some of our work we've been doing in atmospheric chemistry, and in particular, looking at the oxidation of aerosols. So I really don't need to tell you about the important issue of climate change, especially this week during COP26. But in order to understand the changes to our climate and to assess potential solutions, we need to be able to model the behaviour. Now, this is really not a trivial thing to do, and the picture I show here on the left is actually a huge simplification. There are many interconnected processes and species that are all kinetically controlled and vary across the surface of the Earth. So what we need are good parameters to be able to put into these models to be able to tell what our climate's doing. And today I'm just going to focus on one small aspect of this, which is atmospheric aerosols or dust. On the right hand side, I've got a satellite image here which shows the southern coast of Australia, and you can see there's a small forest fire down the bottom and the plume of smoke coming off the fire. If we look at the clouds over the land, they've got the kind of form and shape that you would expect. But as those clouds interact with the dust plume, sorry, the smoke plume, we see a change in structure of those clouds. They've been affected by the smoke. So what's happening here? Well, in order to understand this, we need to sort of think about how a cloud is formed. If you like doing little demonstrations at home, I highly recommend looking at this video from the Met Office on how you can make a cloud in a bottle. Now, in order to make a cloud, if we take our parcel of air that has a certain amount of water in it, we raise it through the atmosphere, it adiabatically cools as it expands and gets closer to the saturation of water vapour. Now, this process alone in the atmosphere is typically not enough to get the water to condense on its own. Instead, what we need are some sort of surface to act as a nucleation point. And this is where the aerosol comes in. It provides a surface for the water to condense onto the surface, acting as these cloud condensation nuclei. So what do aerosols actually do to the climate? Well, first of all, they have a direct effect. So they can directly scatter the sun's radiation, changing how much of it reaches the surface. They then have a series of effects on the clouds. So if we take a cloud and we increase the amount of aerosol particles that are present in that cloud, we still have the same amount of water. So what this means is that each particle has less water on the outside and they're smaller. Now, these smaller particles have an increased backscattering, and so we see less of the solar radiation reaching the Earth's surface, and this actually has a cooling effect. In addition, these can change the precipitation we see, so it can suppress rain, and it can also change the lifetime of the clouds in the atmosphere. So in short, aerosols can make clouds more shiny, live longer, and less likely to precipitate. Now, this may not sound so bad until you start to think about flooding and droughts, and the idea of changing where rain is falling and when suddenly becomes a lot more important. So what form does our aerosol take? Well, we have the solid core, and then we have this water film on the outside. In addition, we have another thin organic film layer on the outside of this aerosol, and this can come from a range of sources. So it can be from natural sources such as sea spray, or from anthropogenic sources from sort of combustion. And this thin film can change the ability of the aerosol to act as a cloud condensation nuclei, its reflectance and its stability. Now, the atmosphere is highly oxidizing. So these films aren't necessarily stable, and they can react in this oxidizing environment, which can destabilize this outer film. And so what we want to do is understand what how this film should be included in our climate. And in particular, how thick is this film that forms? Does it oxidize? So is it stable? And if it does oxidize, how quickly? If it oxidizes very slowly, then we can essentially consider the film to always be present and be a stable layer. If, on the other hand, it reacts very quickly compared to the lifetime of an aerosol particle, we can essentially ignore it because it's just gone and it's not there anymore. Now, in between the two is where we have a bit more of an issue, because if it is changing thickness during the lifetime of the aerosol, then we need to take into account those changes in thickness in our climate models. So how can neutrons help with this? In particular, we've used neutron reflection to look at these systems. Now, as you've already been introduced to, neutron reflection is a good technique for giving us compositional information as a function of depth from an interface. I've labeled this up as being a solid liquid interface, but it could equally be a liquid air or solid air interface. And we know that neutrons are very good for light elements. So in this case, it means they're very good for looking at that water and the organic film. They're also highly penetrating and non-destructive. So the neutron beam itself is not going to be oxidizing our film, unlike if we try to use X-rays. So how do we turn this into an experiment? Well, if we go back to the model of our aerosol particle, we're going to look at this outer interface. So the interface between the water, our organic film and air. And we use a flat surface to model this behavior. And then we can introduce an oxidant species to see how it affects the film with time. And in this case, we're going to introduce OH, which is a very common and important atmospheric species. Now, we're not just going to use sort of standard water, we're going to use a mixture of H2O and D2O so that it matches to the air. So all of our scattering is going to come from the organic film itself. Practically, what this looks like is we have a PTFE trough to put our liquid in, and when we put the whole thing in a bag, so it means that we can control the atmosphere right around that surface. We introduce a mixture of ozone and water vapor into the bag and use a UV lamp to generate OH radicals in situ. And you can see here a picture of it on the beamline with the light on. Now, by changing the ozone concentration and the distance of the lamp, we can then actually control the rate of the oxidation reaction so that it is suitable for the neutron experiment. So what might we expect to see? Well, we're expecting that the reaction is going to be dominated in the tail region, so the hydrophobic region of our layer. Now, this may be a series of steps kind of eating away at those chains, or it could just be a single interaction. These reactions we're expecting to shorten the chains and make them more hydrophilic in nature. So this will reduce the stability of the film, and we're expecting it to remove it from the surface. So the organic films we're going to use are actually from real atmospheric samples, and we've got three different sources for these. First of all, we've got Royal Holloway University London, which this is a map of the area, so the university is shown with the white blob, and London is just off the map here. This here is Heathrow Airport, and each of the orange lines is a major trunk road. So although this looks nice and leafy and green, this is a very urban environment. Our second source is from Antarctica, so a very remote location. And the third is from just burning wood, so wild cherry tree. So what do we see? Well, this is our data from our reflectometry of these atmospheric samples. In each case, the red curve shows the reflectivity from the aerosol sample. The black is just the air contrast matched water without a layer on the surface, so it's effectively our baseline. And the blue is a blank, so it's a filter treated in the same extraction process as the aerosol, but without the aerosol present. Now, compared to the NR curves you saw in the last talk, these are very boring because we're only looking at the signal from the atmospheric material, but actually this is incredibly exciting because what we've been able to see is signal from real non-deuterated atmospheric material at this surface. And so we've been able to look at how much material we get at the air-water interface from these different sources. So what happens if we now oxidize these? So what we have here is the trend in the amount of material that's on our surface as a function of time. And the vertical dashed line shows when the reaction was started, so when the lamp was turned on. And in each case, we see a relatively quick loss from the surface as it reacts with the OH. And the solid line shows a fit to just a bimolecular kinetic model. how can we then link this to our climate effect? Well, from the neutron reflection, we've shown that we can get the oxidation kinetics and the film thickness. Now, from a separate experiment using laser tweezers, we can get the optical refractive index information for these aerosols, which can be combined into a Mie scattering calculation, and that can then be transferred into a 1D radiative transfer model for the climate impact. So what do we see from that? These are the results of the 1D radiative transfer model. On the vertical axis, what we have is the total aerosol radiative effect. So what this means is how reflective the top of the atmosphere is with the aerosol present compared to without the aerosol present. So anything above 0 means we've made the top of the atmosphere more reflective. So you can see across the board, we've got a positive impact on this aerosol radiative effect, but it does depend on the source of the aerosol, as well as depending on the particle radius. So it's particularly pronounced for the smaller particles. And in addition, it depends on the makeup of how thick the shell is over the whole volume of our aerosol particle. And so what this means is that as our film is reacting, so as our shell is getting thinner, we're actually seeing a significant change in what would be our reflective behaviour. Now, it's great to be able to use these real samples, but they're pretty difficult to source and they're not deuterated, so we don't have a huge amount of signal. So it would be really useful to be able to use a proxy. This shows some data from a very similar setup, but using a deuterated lipid molecule as a proxy for our aerosol material. What we actually see in this case, though, is that there is a lot more resistance to the OH. The reaction is much slower and seems to take a whole series of different steps. So it's almost that eating away mechanism at the tails. So this suggests that a single molecule layer proxy is not a good alternative model for real atmospheric samples. So just to conclude, I hope I've been able to show you that we've been able to measure from real atmospheric samples the NR signal and show that these react relatively quickly with OH in a biomolecular process. Now, if we convert those rate constants and apply them to OH concentrations in the atmosphere, the rate suggests that we do need to include these changes in climate models. And together with complementary techniques, we can relate these changes to what would be affected in the climate. And I've also shown that the single molecule proxies are not necessarily a good model for film stability of these aerosols. And finally, I'd just like to say that this is part of a wider program looking to understand the oxidation of these aerosol particles, where we can look to change the reaction center. So looking at different oxidants, different reactants, and different surfaces. So both the water mineral and water vapor interfaces. And finally, I'd just like to thank everyone who's been involved in this research, particularly Martin King from Moore Holloway, who's been the driving force behind this. Rosalie, who is the PhD student who did the majority of the work I've shown, Andy Ward, who led the laser tweezers experiment at the CLF, and Anna and Neil, who from the British Antarctic Survey, who helped collect those Antarctic samples. And finally, I'll leave you with a satellite image showing a different source of aerosol. So this is the coast of Africa looking across the ocean towards the Americas. And what you can see is dust from the Sahara being blown across the ocean. As it goes across the ocean, it picks up sea spray and being coated in these organic films. So thank you.